So we began structures and materials, looking at the four types of forces that we're mainly going to see in the topic. So compression being the first one, and that's where it's basically a squashing force. Forces are pushing either side. The result is that the overall length is going to decrease as you squash the atoms together. You've got tension, which is effectively the reverse process, where the atoms are being stretched and pulled apart, and therefore we see an overall increase in the length of the material. And then we looked at shear, which is where the forces are acting in opposite directions, but they're not collinear, or not acting through the same, not in line with each other. So it's kind of like when you're using an eraser on paper and it sort of changes the shape as such, sort of squashes it over. And then the last one that we talked about was bending, and that's where we've kind of got a combination of, or can result in a combination of tension and compression on either side of the material. So if we draw in a bent rod, sort of forces acting again not in line with each other. We've got compression on the inside, tension on the outside, where they're being pulled apart from each other. And it's mostly questions that are going to appear will be about the tension or the compression. Bending sort of sometimes comes up a little, but more in the context of an analysis of a structure. So we don't really need to analyse the compression and tension either side. We're looking at the overall effect on the material. Alright, then we went on to stress. So basically stress, we're looking about the amount of force over a given area, and we had stress equal to force over area, newtons per meter squared as the units. Alternatively, it has its own unit called the Pascal, but they are an equivalent unit. The reason for looking at stress is it basically gives us a level playing field, a way to compare how the material will act under force regardless of its size. Another definition that came along with stress was strength, and that was stress point of failure. So it's the maximum amount of stress it could take until the material fails. And because obviously we don't want to take a material to the point of failure, particularly when we're building, that led to the idea of safety factors. What that means is, so for, let's do an example, e.g. safety factor 5 means 1/5 the stress as max. So subject it to up to only 1/5 of that stress, so that we don't take it to a point where it could fail. Basically, it's protecting the public from injury, protecting the company from liability of injury caused due to their design failing. And then obviously to come with this was the idea of composite materials. The reason that we use composite materials is you want the good properties or the useful properties from multiple materials. Okay, the most commonly used one is reinforced concrete, and what we're after is concrete is let's go concrete compression, excellent, tension, not flash. So we put steel bars and their tension is great. So where the concrete is going to, wherever that slab is going to experience tension, that's where we want to reinforce it with the steel bars. So for example, basic bridge structure, it's going to be in tension at the bottom. So you would want to run your steel bars along the bottom where it's going to experience tension. It's going to be strong up here where the compression, down here you're going to have your cracks appear if we don't have something that's going to withstand the tension that it's experiencing. A question that comes up, or a style of question that comes up commonly, is where there's a bit of overhang, or a variation to just your standard bridge. So then you need to consider what parts are going to be in tension. Okay, we've still got tension down the bottom there, but in this little bit of overhang we're going to have tension at the top where it's bending down. So we've sort of got, if we over exaggerate the shape, we've kind of got this happening. So we've got tension here and we've got tension there, and the ideal would be to actually ensure that they overlap. Okay, so multiple choice question asking exactly that, giving you different scenarios, which one would be the most appropriate for that type of structure. So following on from that, we looked at strain. Now strain is the change in length over the original length. So be really careful with the information you're given. Make sure you're looking at the change in length, not the total length that you're left with. So do the calculation if you need to. And there are no units for strain, because we're doing a length divided by a length. What you must ensure is that it's a consistent unit. So you either need centimetres on top, centimetres on the bottom, metres on top, metres on the bottom, millimetres and millimetres. Always the same units. So same units in equation. That's the essential thing. So beware if you're given a length of a rod that's in metres and then the change in length is given in centimetres. Make sure you make the conversion of one of them. Okay, how much strain is experienced by the object will depend on the stress. How much force is effectively being applied is what's going to determine how much strain will the object will experience. putting these two together led to Young's modulus. Basically, this is an independent way of comparing properties of materials. Okay, what this does is eliminates factors of size and shape. So you can compare different materials without having to worry about the conditions that they're tested in terms of the shape they're using and how they're, you know, what sort of diameter of the rod or anything like that. So basically, most of these questions we tend to get a graph with, where we are graphing the stress and the strain. Key areas include our linear region, which is the elastic region. If it's a brittle object, it's only going to have an elastic region. Once it gets to the end of its elastic region, it's going to break. At the ends, so that breaking point there, if it's a brittle object, this is called the elastic limit. So once we exceed this, either the object breaks if it's brittle, or it enters the plastic region. Okay, and it may have some sort of bending like that. So this is our plastic region. It's no longer a linear relationship between the amount of force and how far it's going to stretch. Okay, where's my pen? Over here. So at this point, it now breaks. Okay, maximum stress you'd take off the graph is just the highest point that it reaches at any given stage. From my dodgy drawing, that's going to be our maximum stress. Now, Young's modulus, we're basically looking at this elastic region. So we've got Young's modulus is the gradient. It is stress over strain. And basically it measures its stiffness. Okay, it gives us a way to compare how easily a material stretches. So, greater gradient. So we've got material 1 and we've got material 2. Material 1 is not as stiff as material 2. So material 2 is stiffer. It's also stronger. Higher stress is a stronger material. And then higher gradient indicates a stiffer material. It's much harder to stretch it. So just to reiterate, brittle, no plastic region, and ductile. ductile are things that can be drawn into wire, that can be stretched. So once you pass that elastic limit, it will stretch, but it won't return to its original shape. And coming back to our elastic limit, linking to what we were talking about before, safety factors, ensuring, once we get outside our ideal lab conditions, ensuring that we don't have a structure that fails. Safety factors are calculated using the elastic limit. Okay, so rather than saying, well, let's sort of take it all the way up to the elastic limit and scale it back. How about up to the breaking point and scaling it back? Let's just go within the area that we know that it's not going to deform, and then scale it back from there, just as a safety precaution. Strain energy. Can pretty much expect a question on this in your exam. Just a special welcome to Jacob, who's decided to join us this morning at 10:30. Sorry to get you out of bed so early, Jacob. 10:27, sorry, I didn't mean to exaggerate. Strain energy. We find this found under the stress strain graph. So that particular area, that is an A, area under the graph equals strain energy per unit volume. Okay, remember that the Young's modulus graph is independent of shape and size. So finding the area under the graph will give you the strain energy per meter cubed. So if we have some graph, if it's got a plastic region, if it's not a brittle material, this type of question is one that you will do a calculation of total number of squares, add them up, multiply by the value of each unit, or each, look at the scales of the graph, work out the value of one block, multiply it together by the number of blocks. Okay, so that gives you joules per meter cubed. So you're going to need to multiply by the volume of the material to determine the actual energy that's been stored. Okay. Whoops. Toughness. When we're talking about toughness, again, this is linked to the strain energy. So those that are plastic tend to have a plastic region. Those that are ductile tend to be a tougher material because they'll withstand a greater amount of energy before they actually fail. So what we're saying there is greater area under the graph going to give us a tougher material. Alright, probably the most complex part of this topic was looking at the equilibrium conditions and calculating forces within given components of a structure. So, equilibrium conditions. Now, the term equilibrium indicates or hints at all forces being balanced, i.e. sum of the forces equals 0. And the way that we use this is we introduce the concept of torque when calculating, looking at structures. So torque is force times the distance, and we want all of the clockwise torques to be balanced by the anti-clockwise torques. So we looked at a concept called taking moments. So we'll have a look at an example. We've got support A. We've got our bridge. We've got support B. The bridge acting through the center of mass. We've got, let's say, 500 kilogram bridge that's 4 meters long. The time is 10:20 and Jacob is on his way to school. He's 1 meter from the end, only 1 meter onto the bridge, and Jacob weighs a healthy 70 kilos. Alright, so what are the forces acting on each of the supports? We have two forces. We've got the force that must act up at support B, and we've got the force that must act up at support A. We don't know the value of either of these forces, A or B, so we need to eliminate them. So the way that we do that is we take moments about, well, let's just pick one for starters. Let's start with take moments about B. That means if we make point B the pivot, what force or what torque, what clockwise torque, if B was the pivot, that would make our bridge swing around in a clockwise direction from force A. What torque from A would be required to balance the torque provided by the weight of the bridge plus the weight of Jacob on the bridge there? Because the distance from point B is 0, that means the force or the torque provided by the force at B must be 0. So we look at clockwise must equal anti-clockwise. So the clockwise one is the force of support A times a distance of 4 meters, we said the bridge was, must equal 2 meters times the 500 kilograms, which of course is 5,000 newtons. Don't forget to convert to newtons, plus 3 meters, 1 meter from support A, that makes it 3 meters from support B, 3 meters times the 7,000 newtons. Therefore, F of A must equal, what have we got? We've got 10,000 plus 2,100. So does that make it 12,100 over 4? So dividing by the 4 meters to support A. That gives us the force at support A, which will be 3,025 newtons. We've got two options here. We can repeat that, take moments about point A, and then we're going to have this time the clockwise will be 1 meter times the 700 plus 2 meters times the 5,000 must equal 4 meters times f of b. So it's the same process we did. We've got anti-clockwise from B, we've got clockwise about pivot point A from the person and the bridge. And when we can finish that calculation, or we could do a sum of the forces. F of A plus F of B, those are our upwards forces, must balance the downwards forces of 700 and 5,000. So F of B, therefore, would be 5,700 minus 3,025, which we would get a value of 2,625 newtons. It makes sense that the force at support B will be less than support A because there's more weight closer to support A. And if we did that, that's a good check when we actually calculated the value for our moments. If we did it this way, we'd end up with 10,700 divided by 4. Hopefully when we divide that by 4, we get the same answer there. When those answers are the same, we're confident we've done it right, you get your right answer from your multiple choice. The other thing is for bridges involving truss systems. That's our triangular systems. So it's looking at these and trying to work out which of these would be in compression, which of them are going to be in tension. If we kind of think about it, we can do a little bit of just sort of a logic thing. If we've got weight acting down here, that's going to stretch this one, that's going to cause that one to be in tension. Same deal on the other side. That's in tension. It's also going to be pulling these ones down, causing those to be in tension. As they're pulled down, it's going to squash this one at the top, which is going to be in compression. As same deal with this, will be squashed and in compression. Now we don't have to just analyze it that way. That's just sort of one way of just, I guess, logically looking at it and saying, hey, what's going on? But if we had to actually calculate values on my nice symmetrical bridge, then we'd be looking up here. We've got a reaction force from this component here. Then to balance that out, we're going to break this one up into vectors. This one must have a downward component to balance that. So the sum of the forces up must equal sum of the forces down. So to have a downward component, this one must have a reaction force that's pushing that way. So therefore, reaction force pushing out means it's in compression. So it's got vector components to the left and down. And of course, not only forces up, forces down must be in balance. Sum of the forces to the right must equal sum of the forces to the left, or it's not in equilibrium. So based on that, because this has a component to the left, that means that it must have a component to the right. The reaction force here is pulling back in, therefore it's in tension. My bridge just disappeared, so we're now in tension. So reaction force there is in tension. And then we can step around from beam to beam. And we look at this and say, okay, well if that's in compression there, it's also got a reaction force that's acting out there. Based on that, it needs a downward component. This one's got an upwards component. This one therefore needs a downwards component. So we now have tension based on the fact that that's going up. That one must have a downward component. And if we notice, our compression in the left beam and the tension in the right beam are both acting to the right. Based on that, we must have a reaction force. Why do these bits keep disappearing? We must have a reaction force acting to the left to balance those two out, therefore putting that in compression. And we can continue that on joint by joint by joint to work out whether it's in tension, whether it's in compression. If we look down the bottom here, this one's in tension. This one will also be in tension if we work backwards. The upward forces there are balanced by the weight force, the force caused by the mass down here. And then we're going to have horizontal components cancelling each other out as well. So we'd have tension, that would result that being tension, that's in tension. We already know that's in compression, acting that way. Based on that, that's a downwards, therefore that needs to be an upwards, that's a compression. And we have now reaction force on this side. So just going by joint by joint by joint, have a looking at forces up and down, balancing those out, forces left and right, balancing those out. You can work out whether it should be in compression or tension. That's about it. I think best thing from here is to actually start looking at some questions, so we'll get on with that.